Hello, my name is Evan, and today I'm going to talk about our work StyleGenes, discrete and efficient latent distributions for generative adversarial networks, or GANs for short. A GAN is an interplay between two subnetworks, a generator, which translates random noise to an image aiming to resemble the real distribution, and a discriminator, a network that is trying to tell apart fake from real images. This training of adversarial objectives gives us a generator network capable of synthesizing samples almost indiscernible from the real ones. A lot of research in the recent years was focused on improving the architectures of these two networks or refining the training objective. However, the approach for sampling the noise remained largely the same, sampling from a continuous prior. In this work, we aim to design an approach that samples from a discrete distribution to achieve a more disentangled latent space, and do this in an efficient way. How can we design a discrete latent space? A naive way to tackle this task would be to create a single codebook. Here, every image we want to generate would have a corresponding entry in the codebook. We can see that this would easily break the promise of generative modeling to be able to synthesize countless new samples. What would happen if we want to generate millions or billions of images? The memory requirements would quickly explode. How can we create a large codebook that is not memory hungry? We introduce our style genome. We take the codebook and break it down in an ordered set of smaller codebooks. To generate, we sample indices independently for each codebook. We use these indices to look up the corresponding embeddings in each codebook, and then we concatenate them together. Finally, we feed the latent code and continue with the adversarial training as usual. Both the generator and the codebook are simultaneously optimized. Note that with our approach, we can sample n to the power of m unique indices. Some useful insights. We can improve the perceptual quality and variability of our results by increasing the number of entries in our codebook. This makes sense. The same would happen if we were to use the naive codebook. The problem, though, is that this increases the memory requirements. We can also improve the performance by increasing the number of codebooks while keeping their concatenated size the same. This way, we boost the performance. However, we do not use any extra parameters. Our approach could be used as stand-in replacement to the continuous sampling for any GAN-based method, and we experiment with some different ones. Here we show the quantitative results of our analysis. Increasing the number of variants or codebook entries improves the FID score, but also increases the memory requirement of our approach. Increasing the number of codebooks or genes improves the quality while keeping our approach efficient. We test our approach on various datasets. For StyleGen 2, we substitute the StyleMapping network with our style genome and achieved similar results. For projected GANs, we use StyleGenes instead of the continuous prior and report improved FID scores. Our formulation gives a straightforward way to analyze the latent space, so we try to answer the question, which genes affect which attribute? We first generate 500,000 images using our model. Then, we use a pre-trained classifier to predict 40 different face attributes for each of the generated images, and we approximate the expectation of a specific variant to yield a specific attribute like a smile by aggregating statistics. Most attributes are affected by only a handful of genes. For instance, number 66, the gene number 66, affects gender-related attributes, whereas number 85 encodes the movement of the mouth region and is associated with high cheekbones or smiling attributes. However, gene 14 doesn't seem to do much on itself. Actually, most of the genes don't change much when we only change the values for one of them. However, if we are to change a lot of them, Together, we will end up with a novel face. Our formulation gives us a straightforward way to do this analysis, and we can use the same analysis to conditionally sample from our unconditionally trained model. To further increase the likelihood of sampling codebook entries with high probability of the conditioned attribute class, we scale the estimated statistics with a temperature parameter, T. Smaller values for T enforces the presence of the attribute in question. However, if we take this to the extreme, we're gonna sacrifice variability in our results. Moving forward, we also try our approach for interpolation and image inversion using pivotal tuning inversion. Note that our values are values from a discrete codebook, but the values themselves are real values. That means they lie on a manifold that we can interpolate between them or use pivotal tuning inversion to project a real face into our latent space. That was all from me. Thank you very much for your attention and feel free to reach out for any questions.